folks, the video's on.
Yeah, that's true.
Did you do okay on the exams? The exam, singular? Okay, good. Good. No major problems, folks? Let me grab my glasses, because that's not a good lecture without my glasses.
That's all I remember.
Okay, so we are in the middle of our means chapter. And we started naming a few things. Does anyone have any questions on this slide before we move on to the next one? We're good here? Okay, so moving on to the next one, let's go ahead and name these compounds. So if we were to do the first one using common nomenclature, remember we're gonna name each of the things connected to the nitrogen as a branch. So if we had three CH3, so if we had CH3, CH3, and CH3, instead of the cyclic structures, we have trimethylamine. Does that make sense, folks? Okay, so I know you guys see the rings there and you're like, oh, I don't know how to do that, but yes, you do. If there were three methyls and that made up trimethylamine, then this one's gonna be what? And just start with the first part of it. Try. It's gonna try something, right? Okay, so try, and what is this branch right here? It's a cyclohexane. Is that okay with us? So if it was a branch, instead of being called cyclohexane, it would be called what? Cyclohexyl. Just like if it was a straight chain, instead of being called hexane, it would be called hexyl. Or instead of ethane, if it had two carbons, it would be called ethyl. Does that make sense, folks? Okay. So we're gonna have a tricyclohexyl, and then what? Amine. You all right with that? Kind of, sort of, maybe? Last week was a really long time ago, and we don't remember? Okay, we'll get back in the groove of this. All right, so if we were to do a UPAC, recall we have to identify which one of the branches that's attached to the nitrogen is the biggest one, and we're gonna name that as the parent. And when they're all three the same, that seems really weird to name one of them a parent, but that's how we do it. We also have to identify that the branch is connected to the nitrogen by putting what at the front of the name? A big N, okay? And if you have something other than a hydrogen, you have to identify it. Now, do we have two branches hanging off of that nitrogen where we could put an N and an N at the beginning of the name? Yes. So how about we just identify this cyclohexyl group right there as the parent, and then these two right here are gonna be our branches. It's really weird because they're all three the same. So I understand that, folks. But if they were all different, it would be easier, and that's weird too. But anyways, okay, so what I'm gonna start at the beginning of name it for IUPAC? NN. So it's N comma N, and those are capital N's. And remember, this is like a numbering system. So if we had a couple of cyclohexyls hanging off of a very large alkyl chain, and they were on carbon number 3, we would say 3, 3. Okie dokie, Smokies? Yes, no, maybe so? Okay. Now we have 2 of them that are the same there. So we're gonna put a hyphen and then what? Dicyclohexyl. Now we didn't put tricyclohexyl because in a UPAC, one of them has to be the parent. And they were all 3 the same. So again, it's weird. I understand that. But the one in blue, we decided that one is going to be the parent. Could we have chosen any of them? Absolutely. Okay, so we have NN dicyclohexyl, and then what? What's the parent? The parent is cyclohexane, and then we chop the E off the end, and we add what? Amine. So I don't know if I'm going to have enough room here, but it's NN dicyclohexyl, cyclohexanamine. And there's no space right there. I just ran out of space. So NN dicyclohexyl, cyclohexanamine. Okie dokie, Smokies? So in this case, it's probably the common nomenclature that seems to make a little more sense, right? Yeah, a little bit easier on us. Okay, so then let's go down to the bottom one there. And if we do the bottom one, not the bottom one, the middle one, if we do the middle one in IUPAC, we can see how it's probably a little bit easier to name this if we have 3 different branches, because then we're not going, oh, they look all the same, so why is there a parent in 2 branches if they're all the same? Well, yeah, it looks more apparent here. So which one of them is the parent? The methyl, the ethyl, or the cyclohexyl? So this one's the biggest one, right? The longest continuous carbon chain is connected to that nitrogen. Are we okay with that? Okay. All right, so the branches that we have are methyl and what's that one right there? Ethyl. Okay, so we need to start the beginning of the name with what? We could do NN, but we don't have 2 branches that are the same. So you're only going to do NNs together if you had like a di or a tri. But we have 2 different ones, so we have to split them apart. And so we're going to have N-ethyl and N-methyl. So which one's going to come first, the ethyl or the methyl? Ethyl, why? Alphabetical. So we're going to do N-ethyl. Keep going for me, folks. N-methyl. And then what? Cyclohexanamine. And there's no space there. I just ran out of space on the end, so you can squish them together if you have room on your paper. So we have N-ethyl, N-methyl, cyclohexanamine. So do you see how it was a little bit easier for your brain when you had 3 different groups rather than 3 of the same? Okay, good. If we were to name this with common nomenclature, remember we're just going to name each of the branches and put them in alphabetical order. So we have ethyl, methyl, and cyclohexyl. So who comes first? Yep. So we have cyclohexyl. Keep going for me, folks. Ethyl, methyl, and you just put amine on that, right? Yes, no, maybe so? Okay. All right. Are we okay with that, guys? Okay. All right, the very bottom one, what do you notice about that one? something slightly different about this one?
There's two nitrogens.
Yeah, there's two nitrogens, so it's gonna be some kind of diamine. Does this sound slightly familiar, folks? No, okay, well, moving on. What's the longest continuous carbon chain there? How many carbons? So, two of us said 3, but if we do this, is it 4? Yeah, it's just drawn that way to trick you, right? So most of us would like there to be 4 carbons in a row and have the NH2 poking up like that instead of drawn that way, but we've got to get used to that. So what we have there is some kind of diamine. Now, the question is, are we going to number forwards or backwards? If you number forwards like this, 1, 2, 3, 4, you're gonna have your nitrogen on carbon number 1 and the nitrogen over here on carbon number 3. If we number backwards, you don't start with your nitrogen until carbon number 2. So then you would have a 2, 4 instead of a 1, 3. So we're gonna do 2, 4 or 1, 3? 1, 3, good, good. Okay, so we have 1, 3, I'll start you folks there. This is IUPAC. Common we usually only use when it's a pretty simple compound. Okay, so we have 1, 3 here. We don't have NNs because we don't have a single nitrogen with a bunch of things bonded to it. We just have a couple of NH2s on this one. So we have 1, 3, and what is the parent chain name? Okay, so we're identifying that we need a di in there somewhere, right?
Yeah.
Okay, and it's a butane, right? So what IUPAC says is you're gonna do butane diamine. And the E stays whenever you have that Greek prefix there. Do we kind of sort of remember that?
Yes.
When there's no Greek prefix, the E takes off, but when there's a Greek prefix, the E comes back. We remember that part? Super fun, right? Okay. Any questions on this, folks? Moving on? Okay, so let's draw some. Because drawing is generally easier than naming, right? Okay, so we have N-ethyl, N-methyl, propylamine. So what letter are you gonna draw first? You're gonna draw a big ol' N, right? And you're like, okay, so I got an amine here. And I've got N-ethyl and N-methyl. So I can just go ahead and draw a couple of things on my nitrogen. Okay, so the ethyl, what does that look like? Yeah, CH2, CH3. So that's your ethyl. And what does methyl look like, folks? There you go. So right now we've got our ethyl and methyl. And what else do I need? Like that? Yes, now maybe so? Okay. All right, so N-methyl and prime propyl, 1,4-butane diamine. Anyone want to attempt this one? Okay, so what does butane look like, folks? 4 carbons. So let's start there and do 1, 2, 3, 4. Okay? So start right there. So 1,4-butane diamine. So what do I want to bond to the first carbon and the 4th carbon? Yeah, so I want to do an N and an N. And when I had it drawn like this, you don't want to put a nitrogen here and a nitrogen there, because what did you just do if you did that? Yes, you remove 2 carbons if you did that. So again, what I'm talking about is if we had this, which is what I originally drew, and you put a nitrogen here and a nitrogen there, you're only left with these two carbons. So you wanna make sure that you don't do that, and you retain your original butane. Does that work for us? Okay, so notice that I didn't draw NH2s, I just left it at ends, and that's because I want to stick what on there? Okay, I have to have put a methyl and a propyl somewhere, right? Now, your nitrogens are on the ends, so does it matter which one is the N and which one is the N prime? Not really, okay? All right, so if we wanted to be super technical, we go like, okay, the methyl comes before the propyl alphabetically. So what we're gonna do is put the methyl on the first one, and there's an H there that we just assume we know is there. And then on the other side, I'm gonna put a what? A propyl. But if I drew this without the numbers there, it would look exactly the same if you flipped it around. So for this one, it doesn't really matter which one is the N and the N prime, because you have a propyl on one end and you have a methyl on the other end. Okie dokie smokies? Okay, P-aminophenol. So you've got phenol here. Does anyone remember what phenol is? Yes. So when you have phenol, that's a benzene ring with a what? Two benzene rings? Oh, I see what you mean. Yes, when benzene is a branch, we switch it from benzene to phenyl. But this one is phenol, so it's a benzene ring with what on it? Anyone? An OH. Do you remember that? So you're on the right track there, yeah. Okay, so at this point, I can put the OH on any of the carbons that I want, and it'll be phenol. Are we all right with that? You could have put it on the bottom if you want. But now you have to specifically put your amino group somewhere. And where are you gonna put it? What does P mean? Yes, that's the 1-4 relationship. So we have ortho, meta, and para, or OM and P, and O is a 1-2 relationship, and M or meta is a 1-3 relationship, 1, 2, 3, like that. And P is a 1-4 relationship. So amino, when it's a branch like that, it means what? What do I draw on the bottom there? NH2, okay? If it was NO2, that would be nitro. Are we okay with the difference? Okay. Now the OH took precedence over the NH2, so that's why the OH gets the parent designation and why it's not amine, and the amino group, or the amine group, goes to the front of the name and it becomes the branch. Are we all right with this, folks? Kind of, sort of, maybe? Okay, so moving on to the structure of our amines. So the amine has a specific structure where we have a tetrahedral geometry if we're talking about electron pair geometry, and if we're talking about where the atoms are placed and we are ignoring the lone pair up there, it's going to be called trigonopyramidal, okay? So when you were in 2A, you might have learned that this was tetrahedral because we were talking about the arrangement of the electrons around the central atom. But if we ignore the lone pairs on the top and we just look at the atoms, then that's a different geometry categorization, and we call that trigonopyramidal. So both of them are the same, it just depends on what you're talking about. So do you guys remember the whole tetrahedral thing? Kind of, sort of, maybe? So things are arranged as, in tetrahedral formation, they had a bond angle of about 109.5. Does that sound familiar? And then you would have seen ammonia And then you would have talked about how the lone pairs in ammonia, which is NH3, folks, squish the bond angle down to about 107. Does this sound familiar? And then you might have moved on to water, which has 2 lone pairs. Sometimes we draw the balloons around them, and that squishes that bond angle further to 104.5, or some professors or books say 105. Is this jogging your memory? Okay, good. Anyways, what I wanted to say is you folks have seen something like this before, okay? So, any questions on this? We're okay? Yes?
So when are the times when we're not supposed to use try? Because I noticed you use instead of try, use another method of the maybe similar to try. Like for example, dye, you use butene.
Are we going back a couple slides?
Well, based on the name, basically.
Oh, up here, okay. So, you see how you have 3 methyl groups?
Yes.
So that's just trimethylamine, it's the common nomenclature they're using here, okay? And then the one on the top, there's only 1 methyl group, so it's methylamine.
Makes sense.
Okay. Anybody else have any questions on this slide? We're good? Okay. Alright, so what would happen if we tried to say, okay, do our amines have enantiomers? Well, if you look at the molecule on the top left, and then you do the mirror image of it, you might try to move it around and see that you cannot superimpose the mirror images on each other and say, okay, then I have enantiomers here. The problem is that the lone pair electrons are contained in this p orbital right here, and do we remember sp, d, and f orbitals? So your s orbitals were spherical, and your p orbitals were dumbbell shaped, and then your d orbitals were crazy, and your f orbitals were even more crazy, right? Okay, so because the lone pair electrons are in this p orbital, they like bounce back and forth, and what that does is, so say you have these atoms down here like that. When these bounce down here, the electrons that are pointing down are like, oh, you're taking up too much room. And it's like an umbrella that the wind hits it and it pops back up the other way. So it's like, whoa, and it goes back and forth like that. And so you can see it here, it's drawn planar here, and then you can see that it's popping back that way, or doing this. So you don't get one or the other. So if we were saying that's one enantiomer, well, they're gonna flip back and forth. So you can't resolve the 2 because they go back and forth. So you're not gonna have enantiomers here, even though it'll look like it on paper. Does that kind of sort of make sense? Okay, so we don't have to do, is this an enantiomer of this one in the amine section? Okay? Yay, right? You guys look so excited today. Okay, physical properties of amines. Hydrogen bonding. So hydrogen bonding is going to increase their boiling point because hydrogen bonding keeps the molecules close together. So we got to put a lot more energy in to get them apart, which translates into cranking up the temperature there. So our nitrogen-containing compounds, so what we've got is we've got a lone pair on that nitrogen. And also what we have is we have a hydrogen that's bonded to a very electronegative atom. So if you have an electronegative atom in one molecule, and you have a hydrogen that's bonded to a very electronegative atom in another molecule, then you have hydrogen bonding. And if you get a bunch of these together, they all like to hydrogen bond just like water does, and so you get a higher boiling point than, say, if you had something that had a similar molecular weight, like pentane over here. So can we see how pentane does not have any electronegative atoms in it? Like oxygen or nitrogen? No answer. Okay, about 36 Celsius. But the boiling point of a similar molecular weight amine is 56. So we definitely have an effect of the hydrogen bonding there, keeping those together, away from the vapor phase. Okay, folks? Yes, no, maybe so? Okay, so down here it says our low molecular weight amines tend to be water soluble, whether they are primary, secondary, or tertiary. If you have fewer than 5 carbons, you're usually soluble in water. Once you start getting longer R chains, hydrocarbon chains, you tend to get more insoluble in water. And that should make sense to us because hydrocarbon chains are nonpolar. And water is what? Polar. So if you have a big old long non-polar chain and a little tiny bit of your molecule is polar, you're gonna swing more towards the non-polar side, right folks? And water is gonna be like, I'm not very attracted to you. Just how it works, right? All right. You guys look so excited. I'm thinking about like, oh my gosh, I'm just trying to make it to the Thanksgiving break. Is that what we're doing? You need me to go back?
No, I have a question about that. Is it only 2 days that we're off on Thanksgiving?
No, we get the whole week. And there were people who didn't want the whole week. And we all had to like debate it for like years until people were finally like, all the kids have it off and the students never come anyways. And yeah, so there were actually people who didn't want it off. So yeah, those of us who wanted it off were like, people are crazy. So anyways, you're welcome. So looking at some of our amines here. Apologies for the little bit of fuzziness there. I found this picture like forever ago when it was like teaching by PowerPoint was like the new thing in the technology. And I haven't found a better chart since. I should probably just type all of this stuff out. But by this time in the semester, I'm like, I don't want to do that. Okay. So looking at our primary amines up at the top there, all the way over to the water solubility, you can see they're very soluble. And that's because our hydrocarbon chains are little, and so your electronegative atom there is dominating. And if you have an electronegative atom, that means you're causing polarity in your molecule. And if you're polar, is water going to be attracted to you? Yes, that means you're going to be soluble. So does that make sense? Okay, so if we start getting larger, let's see if I can find a big ol' one. We're just doing primary, secondary, and tertiary here. Okay, I was looking for a big ol' long one. Insoluble. Diphenyl, okay, slightly soluble. Okay, I guess it'll be on another slide, the one where I have a big ol' long one for you. Okay, so talking about primary versus secondary versus tertiary amines, the primary and the secondaries tend to be more water soluble because they're hydrogen bonding. With our tertiary amines, we don't have that hydrogen on the nitrogen to do the hydrogen bond. So let me draw that for you folks. So we have the electronegative atom right here that can hydrogen bond with the hydrogen of another molecule that's on an electronegative atom, but it doesn't have the hydrogen to do the other half of the hydrogen bonding. So if it meets another one, what happens is this one is like, hey, I want a hydrogen bond. Do you have any hydrogens that I can hydrogen bond with? And this one's like, no, I'm looking to hydrogen bond with somebody who has a hydrogen also. Neither of them have a hydrogen on their nitrogen, so they can't do the hydrogen bonding. So if you look down here, you can see the slightly soluble and the slightly soluble, so that's kind of what's going on there. But if you put them in water, which has a hydrogen that can hydrogen bond, it can do it, okay? So that's how it's gonna dissolve those tertiary amines there. Okay, let's see, what I'm looking for, insoluble here, diphenylamine. These ones are kind of big. Your diphenyl, okay. So it makes it really hard to hydrogen bond there because those little benzene rings are kind of like, whoa, and they're keeping those from interacting with the water molecules that are trying to dissolve it. So yeah, the diphenylamine right here tends to be pretty insoluble because the water can't get in there to that nitrogen to do the hydrogen bonding and the attraction. Questions for me? No? Okay, moving on. Let's do some reactions, folks, because we love reactions, right? No answer. Okay. So amines, they are basic, folks. And when we did experiment 22, you would have filled out that column that said basic, basic, basic. You remember that? And I was like, if they're all basic, that's okay, don't freak out. Because I know students, you guys want like a variety of answers. Yeah, okay. All right, so what happens? You throw them in water, and right here you have lone pair electrons, and this reaches over to the water and it's like, give me that, to the hydrogen. And the water's like, oh, okay, you can have that hydrogen. And what forms is an ammonium ion. So the other way that we can write that is NH4+. And we've seen that before. We saw that in the amines lab, experiment 22. And you form this right here, which is called hydroxide. And if you're forming hydroxide in your solution, what kind of solution do you have, acidic or basic? You have hydroxides floating around. That would be H+ floating around. Basic. You're creating OH-, the hydroxide, in your solution. So if you think back to 2A and you remember the acid-base chapters, remember that acids are going to create a solution that has H+ or H3O+. And your bases are going to create a solution that has available hydroxides, OH-. Does that sound familiar? Okay, so what we're used to with bases is things that have a visible OH on them, where you're like, oh, okay, that's a base, because NaOH is going to split into Na+ and OH-, and of course there's going to be OH- floating around in the solution. But amines are sneaky bases, because what they do is they use the water, and the water will create the hydroxide there. So that's a little minus sign right there. Are we okay with this, folks? So the amine doesn't release its own hydroxide. The amines actually look like they might be acids because they have a bunch of hydrogens, right? No? Yes? No? Okay, so watch out for that because amines are bases. So an example at the bottom, we've got a primary amine here. What would we call this thing? Methylamine. Is that okay with us? Methylamine? Okay, we're gonna throw some methylamine in water. And it's small, it only has this one little alkyl branch. So is it gonna be soluble in water? Yeah. Okay, so that nitrogen is gonna be like, hello, here I am, I'm making everything polar because I'm very electronegative. And the water is gonna be like, hello, I am polar too. And polar things like polar things. And the lone pair on the nitrogen is gonna reach over and grab this hydrogen right here. And the water's gonna be like, okay, take it away. And then we get the methyl ammonium ion. And you can see that it has the positive charge outside of brackets here don't worry about if it's put in brackets or not. It just depends on the chemist, whoever is drawing it. So what we could also do is draw it a different way and put the positive charge right there on the nitrogen. Is that okay with us? You could also draw it out like it is. Like that, and just make sure that you put the positive charge on the nitrogen. Now that one at the top there, that is a hydrogen. Okie dokie smokies? Good? Okay. Questions for me? Alright, so if we throw an amine into water and we create hydroxide, what kind of pH are we gonna get? What's that? 14. Okay, so something that's above 7, right? Remember the scale was 0 to 14 and neutral was 7? Do you remember that? And it seemed kind of backwards because most of the time students think that if you have a really strong acid, it's going to have a high pH, but no, it's the other way. It has a low pH, and the bases have high pHs. Does it sound familiar? So we're going to get something on a basic range, okay? 10, 11, 12, all the way up to 14, like you said. Okay, questions for me? Concerns? Complaints? Yay! Okay, so we did amines in water, but what happens when we put an amine, a base, with an acid? So HA is just some kind of like generic acid. So A just means anion. So we could have HCl or HBr or HI, whatever, folks, okay? So again, the lone pair on the nitrogen is going to reach over and grab the hydrogen, and we're going to get some kind of ammonium cation, and then we're going to be left with the anion here. And let me just go ahead and draw the rest of the lone pairs in. And so on this one, gotta like sneak it in under there like that. So if we're doing HCl, which is hydrochloric acid, the lone pairs that are there would look like that. And over here you could draw them in. Again, chemists are lazy and we just assume that you know that they're there and what we're talking about. Okay, are we all right, folks?
Yes.
Can I start on 90? Okay, so when the nitrogen picks up a fourth bond, you're gonna see what kind of charge?
Positive.
You're gonna see the positive charge. So notice that. When you have a lone pair there, nitrogen is doing exactly what it wants to do. It's got an octet, 2, 4, 6, 8, and nitrogen likes 3 bonding pairs and a lone pair. Over there, it's got 4 bonding pairs. So it's got its octet, 2, 4, 6, 8, so it can do that, but it's not doing what it prefers to do. So you see a difference in charge. So it goes from a neutral to a positive there. Now, if you have neutral and neutral here, and you create something with a positive charge here, you have to also create what? A negative charge, because remember the conservation of charge? So not only do you have to have the same number of atoms on each side, you have to have the same net charge on each side. So if you have neutral and neutral, which is 0 charge and 0 charge, and we create a +1, we have to create a -1 to counter that, because +1 plus -1 is what? Oh no! I promise you know math in this class, and I'm asking you to do negative numbers, right? So a +1 and a -1, folks. 0. Okay. So are we okay with this? Kind of, sort of? Okay. You will be on Wednesday, right? No answer again. Okay. All right. Problems, folks. Let's draw the product for the following reactions and name the products. Okay. So first of all, for the reactant there, we have a nitrogen that's bonded to three ethyl groups. So if we were to name that in common nomenclature, what would that be called? Triethylamine, right? Are we okay with that? Okay. All right, so we have an amine that's going to react with water. So what we looked at before on two different slides was what happens if we have an amine and we drop it into water, and the other one was we have an amine and we react it with an acid. So this one is the amine with water. And let's go ahead and draw the lone pair on the nitrogen there, just so it jogs our memory. So the lone pair on the nitrogen is going to reach over and grab what from that water? Yes. So you can just go ahead and draw it exactly the same concerning the ethyl groups, and then plop a hydrogen there. And then you can draw brackets around it and put a positive charge on it, the outside of the brackets, or you can put the positive charge where? On the nitrogen. And you can circle it or not circle it. I just circle it so you can see that it's there. Okay, so this one right here is called triethylamine. And the product is triethyl ammonium. Or you can call it the triethyl ammonium ion or the triethyl ammonium anion. And where does that come from? We're back here, and it comes from the basic ammonium ion. So NH4 plus is the ammonium ion. So what we just drew was some kind of derivative of the ammonium ion, where we plucked off those black hydrogens and we put ethyls in their place, okay? So that is your triethyl ammonium ion. Now, the other product is gonna be what? OH minus, yep. So you can draw it that way, or you can draw it this way, or you can put the lone pairs in. And you can put the charge on either side. The negative charge is going to be more centered on that oxygen because it's the electronegative atom. So it's like, come here to all of the electrons. Okie dokie smokies?
Yes.
Okay, so you folks told me that that guy is named hydroxide. All right, so the example on the bottom, we have an amine reacting with an acid instead of reacting with water, but it works pretty much the same way. The lone pair on the nitrogen right here is going to reach over and grab what? The hydrogen. Come here. Okay, it's going to create some kind of ammonium ion. So we've got, I'll just be consistent here. And what am I missing in that structure? Yeah, the charge. I can draw it out also with the two hydrogens, these two right here, right there, and right there, just so you guys can see the expanded version of it. And then I'm gonna put the positive charge on the nitrogen, or you can put the brackets around it and put the positive charge on the outside. But what you don't wanna do is put a positive charge on the nitrogen and then draw brackets around it and put another positive charge, because you're saying it's +2 then. You wanna do one or the other. Does that make sense?
Yes.
Okay. So, in the previous example, the anion was hydroxide. So what's the anion for the bottom problem? Chloride, yep. So we have Cl, and in the reactant, it had 3 lone pairs. When the lone pair from nitrogen reaches over and grabs the hydrogen's like, whoa, I can only have one single bond. That's it. I can't have 2 people single bonding to me. So it releases the bonding pair and it turns it into a non-bonding pair, also called what? Lone pair. And so that's what we see right there, and then the other 3 were already there. And what am I missing here? Good, negative charge. You can circle it or you can not circle it. Okay, so some of you already told me that when you have chlorine that has a negative charge, it's called a what now? Chloride, yep. So if this one up here is triethyl ammonium, this one right here is gonna be called what? Yes, that's methyl ammonium. The ammonium portion of the name is saying you have a nitrogen that is single bonded to 4 different things. What is it single bonded to? Well, if you just name one branch, like methyl, it's saying, okay, we've got a methyl on there, and then if nothing else is listed, you assume that the other 3 are what? Hydrogens, okay? And you can also call that the methyl ammonium ion or the methyl ammonium anion. Okie dokie smokies. Questions for me? All good? Okay, moving on. Oh, moving on to a blank slide. Yay, we finished that chapter. Okay, I'm gonna flip over to the lipids chapter. Does anyone have questions on amines before I switch? You sure? You sure you're sure? Going once? Going twice? Okay. All right, folks. So one of our favorite things, fats. Yay! We all love eating those, right? We don't love being that, but we love eating them. So that, becomes a problem, especially when you smell the bacon, because then you just have to eat it, right?
Why can't they just keep it down?
What's that?
Why can't they just stop saying, I'm cause diabetes, this will cause. We just enjoy meat.
Right?
Even water's gonna be bad for us.
Or this week eggs are good, next week eggs are bad. Right? Yeah, bacon, I can't resist bacon. Cheddar and sour cream ruffles too.
I like them in a sandwich.
Cheddar and sour cream ruffles.
No, I'm talking about bacon.
Bacon, oh yes, bacon. Bacon and avocado. Yeah, okay. Alright, so lipids are a little bit different. So our other chapters, we were taking a look at functional groups. So what I mean by that is alcohols, you had some kind of something that looked like that. You had a hydrocarbon chain that had an OH on it. If we were taking a look at aldehydes, what you would have is R and then a carbonyl group and a hydrogen on one side, and ketones, you had R, carbonyl, R, and esters. You have R, carbonyl, OR, and I forgot carboxylic acids, but I ran out of room. So carboxylic acid, how is it different from an ester? Does anyone remember? Yes, instead of that R on the right side, the carboxylic acid has a hydrogen. You guys remember that? Okay, well if you didn't, I just told you, so there it goes. All right, so in each of our different chapters, we took a look at different functional groups and we talked about what it looks like, what it smells like, physical properties, reactions, blah, blah, blah. Well, lipids don't have a particular structure that we can pick out like this. They have a lot of variations. So how we define lipids is different. It's not by structure. So the first bullet point says the identity is defined based on physical properties rather than their chemical structure. So physical properties. So the big one is solubility. Is it soluble in water or not? Now just knowing what you know, lipids, should they be soluble in water? No, okay? So that's a really big one right there. So they should not be soluble in water, but they should be soluble in organic solvents. And by organic, I don't mean like when you go to the grocery store and you buy lettuce that hasn't had fertilizer on it. Organics in chemistry means that you've got a lot of carbons and hydrogens, so stuff that we've been talking about before. So our solvents would be like hexane or dichloromethane, and we've seen dichloromethane in lab because that's how we extracted our caffeine. Do we kind of sort of remember that? And it was a weird one because it was the non-polar solvent, but it sat below the polar one when we're used to oil being on top of water. It was dichloromethane. It was different. It was on the bottom. Kind of sort of remember this? Okay. All right. So, anyways, most of these are biomolecules. They're soluble in organic solvents and insoluble in water. And they contain a lot of carbon-carbon and carbon-hydrogen bonds. And they contain few polar bonds, meaning they don't have a lot of electronegative atoms in them. So you don't see a whole lot of oxygens and nitrogens. You might have like a few of them on the molecule, but most of the molecule are carbons and hydrogens, okay? Because hydrocarbons are insoluble. And then we can go ahead and take our lipids and categorize them into two different groups. So the first one is complex lipids. So these are ones that can be hydrolyzed, and what is that? We'll talk about that in just a minute. And the other category is simple lipids, and these cannot be hydrolyzed. So down here we have steroids, prostaglandins, and terpenes. Terpenes you probably have encountered in something called pine sol. Does that sound familiar, folks? No? Okay, everyone uses Fabuloso? Okay, me too. Okay, steroids we usually know about. Those are cool things to talk about because they have a specific structure. Prostaglandins, these do all kinds of things in our bodies. We'll talk about those. Complex lipids over here, waxes, triglycerides, phospholipids. Oh, there's so much to talk about over here. Triglycerides, we get to talk about those a lot when we're talking about medical issues and heart disease and all of that good stuff, right? Like whether to eat bacon and eggs or not, right, friends? Yes. Okay. So, our hydrolyzable lipids. So these can be converted into smaller lipids by hydrolysis. Hydrolysis. Lysis means what, folks? To break or to split it up. And the hydro part of it means what? With water. Have we seen hydrolysis before? Yes, you have. And this is the same thing that you've seen before. It's just that your R chains are a lot bigger. So if you have a giganto R chain over here and a big one over here, your molecule is going to be mostly non-polar, even though it has this little region right here that has a couple of oxygens. So that is why that might be a lipid there. Okay, so back to taking your ester and hydrolyzing it, which we have seen before. You are in water and you throw in an acid catalyst, okay? You can also throw in a base catalyst, or you can use an enzyme, which is what your body likes to do, right, folks? And an enzyme is a what? It's a protein. Yes, it's a protein. How do you know that? Okay, and what we get is a carboxylic acid and an alcohol. You kind of start to remember seeing this somewhere before. Okay, as long as you remember, like, oh yeah, we did learn that, but not the specifics of it, maybe, like, we're good here, okay? All right, so this is going to happen with our hydrolyzable lipids, and you'll see this in the next slides. Okay, so taking a look at these guys right here. Now, our different hydrolyzable lipids, you can see right here that we have waxes. And what I want you to notice is you just got a giganto R here, and another big R over here, we can call that R prime. So if you have R and the carbonyl group, carbon double bond oxygen, O, and then another R over there, what kind of molecule do you have? What functional group is that? It's an ester. You have seen this before. It's just an ester. So an ester looks like this, folks. The R's can be the same or the R's can be different. We just saw the esters with little R's in the ester chapter. So for the fats, the R groups have big ol' long hydrocarbon chains. And if you have big ol' long hydrocarbon chains, are you going to be soluble in water or not? Insoluble. You're not soluble in water Because the hydrocarbon chains are nonpolar and water is, yes, okay? And that's what makes a wax, which we put on things to protect from water damage, right?
Yes.
Okay, all right. And because these are esters, they are hydrolyzable like regular old esters. And we get a carboxylic acid and an alcohol from that reaction. Are we okay with that? Was that a question back there or a stretch? Okay. All right. So back here we said waxes, triacylglycerols, which are also called triglycerides. And you see that name used right there. Same thing, folks, okay? Just in case I said triglyceride and you're like, that says triacylglycerol. What is she talking about? Same thing, okay? All right, so what we see here is you have an R group, and then you have the carbonyl group and then an O right there, and then you have an R group over here, but your brain is gonna go, ah, because this R group over here has got all kinds of things going on. But just breathe, it's just another R group over there. The thing is that you've got 3 of those going on. Do you see that, folks? You just got 3 esters on the same molecule. Okay? No answer. Okay, all right. So that's a triglyceride. Now, phospholipids. Phospholipids you will hear about in biology because we always talk about the phospholipid bilayer. Does that sound familiar? Okay, so the phospholipid bilayer right here, you've got your polar region. And right here, you've got your 2 tails, nonpolar tails. And so what we see is these drawings, and it goes all the way around, and then we're like, woo, that's a cell membrane. And then you put some big old transport proteins there, and then you talk about blah, 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 right? Yes? Yes, it's just like the mitochondria is the powerhouse of the cell. You see this in every biology text ever written. So, yes, this is very, very important to life, these phospholipids here. Okay, also, in that box, it says lecithin. People who came to the morning lab, does that sound familiar? Nobody came to the morning lab? People who came to the morning lab, we extracted lecithin out of an egg yolk. So you can see here that, yes, it is a lipid, because I was like, we're going to talk about lipids in lecture, just wait, hold on. Here it is. And when I was talking about lecithin, I said it has this polar tail, and it has, this polar head, and this nonpolar tail. Well, actually, it's 2 nonpolar tails, but I just simplified it until we could get here, okay? All right, on the bottom there, it says, in each of the complex lipids below, where is the hydrolysis likely to occur? So I'm guessing that was supposed to be at the top there, and then the chart was supposed to be below. But yeah, can anyone identify where we're doing some hydrolysis here? We scooch back over here. This bond is the one that's broken. Where is that bond in this molecule, please? Is it on one of the ends? No. Maybe towards the middle? Yeah, maybe it's right here. Yes, no, maybe so? If we look at this general equation, telling you right there, between the carbonyl carbon and the OR, that's the one that we're breaking. Okay? All right. And our triglyceride, that's going to occur right here. Oops, sorry, 1 over. It's between this carbon and this O here. So that's right here, and right here, and right here. We okay with that? Okay, so for our phospholipid, we've got it here and here. Does that look consistent for everybody? Okay, based on this general equation right here in this bond. Questions for me? No? We're all right with this stuff? Okay, so what about non-hydrolyzable lipids? So that's nothing fancy, it's just saying that
They can have broken down.
yes, it cannot be broken down using water and your catalyst, your acid, base, or enzyme catalyst. So they're stuck there, okay? So steroids. So there's not just like steroids for sports. We have all kinds of steroids that we'll talk about. And what you'll notice is your steroids are going to have your basic cholesterol backbone, meaning that you have 4 rings that are fused to each other, and 3 of the rings are 6-membered rings, and one of the rings is a 5-membered ring. And these are so common that we call them A, B, C, and D ring. And the different variations of this will give you different steroids. Are we okay with this, folks? Okay, so then we have prostaglandins and terpenes, and notice how on this it gives you fat-soluble vitamins and eicosanoids. We've got our prostaglandins there. This is just a different way to categorize non-hydrolyzable lipids. So here we have steroids, fat-soluble vitamins, and eicosanoids, and back here we call them steroids, prostaglandins, and terpenes. Don't worry about that, folks. I'll let you know what's important there. Now, your terpenes, like limonene, they tend to have a certain scent. The other one I was talking about in pine sol is called alpha-pinene, and it's this cool little box of a molecule. I should get a slide and insert it here for you folks, and maybe get a sample of it so we can all sniff some pine sol, right? Okay, so those are your non-hydrolyzable ones. Okay, so let's talk about each category here. And so we're backing up a little bit to the hydrolyzable ones and talking about waxes. So waxes are esters, and we saw those back here. Okay, we said they're esters. And they're formed from a fatty acid, which is just a carboxylic acid. So it's a carboxylic acid with a long R change. So carboxylic acid looks like this. Right, and it's got a very long R chain on it. So a huge hydrocarbon chain, which tends to make it insoluble. And not only does it have that side, but you put it together with a high molecular weight alcohol. So remember, alcohol looks like that. And when we're talking about high molecular weight, it means that the R chain in alcohol is very long. And if it's very long, it's adding a lot of weight there. So you have a molecule that has 2 very long R chains on it, and so that tends to make it pretty insoluble in water, okay? So our waxes serve a variety of functions, as the bullet point says up there. The first one is communication, second one is protection, third one is water repulsion. So if you think about protection, maybe you can think about how if you wash your car, you might wax it also. It's protecting it from water, because water will react with metal, you'll get oxidation, and you don't really want your car to rust, right folks?
But even wax does that too.
What's that?
Wax also does that too in good time.
Wax rusts your car?
In good time.
Oh, okay. I don't usually wash my car. I'm a dirty car person. People write "wash me" on my windows. I'm like, yeah, I'll get around to that. And then people who like wash their car every weekend, they're like, how do you deal with that? I'm like, I don't know. But my house is clean, so there. Okay, so water repulsion, kind of think of like leaves on the outside outside of the leaves, we have a wax, or also maybe like on a duck, or any kind of like marine, or what's the freshwater called? Aquatic birds. They have the wax on their, I want to say leaves. Whoo, feathers. Because you don't want the water getting into you when you're like sitting on, in the middle of the pond, Mr. Duck, okay? Communication. The example here is a whale. So whales have this large organ called the spermaceti. You can see that right here. It says your spermaceti organ. And they have a bunch of oil up there. And it helps them communicate with each other. Have we all seen those videos of whales doing the whale sounds? Some of us have the Calm app, and we're like, yes, I listen to the whale sounds every night to sleep. Okay, so yeah, the whales used to be hunted for this oil, and people used to make candles and different kind of waxes and all kinds of things from this oil. Poor whales. But yeah, they use this organ for communication between the different whales. So that's what it means up here by communication. And there's lots and lots and lots and lots of different uses for waxes. But the general wax structure, like I said, folks, we've got an ester here. And these R groups right here, are they big or small? They're really big. And how do we get that? Well, we have a fatty acid. And a fatty acid is just a carboxylic acid that has a really long R chain. Does that make sense? Okay, so we've got a carboxylic acid here with a big old long R chain, and then we're going to react it with the alcohol. And the bullet point up there says a high molecular weight alcohol. So that means that this blue R right here is big or small? It's big. So if it's really big, it's making the thing weigh a lot, which means high molecular weight. Does that make sense? Okay, so we react these things together, whiz bam bang, and we get a wax, which is just an ester with big ol' long R chains. And we have seen this reaction before. It's ester synthesis. You guys remember making banana oil in the lab? You made an ester there. So here we're just making an ester with long R chains. So an example of this is we have palmitic acid here, and it's an acid because it's a carboxylic acid. And we're reacting it with an alcohol here, so you can see the R group and the OH on it. And this has got a really long R chain, so you can see the 14 here, and then the CH3. So this has a total of 16 carbons. And over here we see 15 plus 1, so we've got another 16 carbons over there. And we put them together, and you have acetyl palmitate, and this has really long R chains. This is a major component of spermaceti wax from the sperm whale. We okay with this, folks? Kind of, sort of, maybe? Do we recognize that we've seen the ester synthesis before? And the only difference here is that the R groups are big. And we change up the nomenclature a little bit because they have different properties. Questions for me? Nope. Okay. All right. How are we doing on time? 1:56. I have lots of time to torture you. Woohoo! Okay, so let's do this problem right here. So beeswax. So what are the two products formed from the acid hydrolysis of triacondyl hexadecanoate, a major component of beeswax? Okay, so we're doing acid hydrolysis, so that means we're gonna add some water, and we're gonna have an acid catalyst. Are we okay with that, folks? Okay, so this right here, what's the functional group there? Aldehyde, ketone, carboxylic acid, alcohol, ester. It's an ester. So what we're gonna get is a carboxylic acid and what? Yes. Oops, that's the backwards one. Right there we were doing how to put it together. ester and we make carboxylic acid and an alcohol. Okay, alcohol. All right. So this side right here, you can see that it says it has 16 carbon atoms. So what we want to do is you want to say CH3 and then put CH2 in parentheses and then do your carbonyl group and OH. And yes, I have forgotten something, don't worry, I'm coming back to it, okay? Does that look like the basic structure of a carboxylic acid, folks? Okay, so we've got an R chain over here, we've got the carbonyl, we've got the OH. Now what number do I need here? How many CH2s do I need? Okay, hold on, because this says 16 carbon atoms total. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So your 16th one is this one right here. And then you're using up another one for the CH3 on the end. So how many go here? 14. Do we see that? Okay. Be careful of that so you don't add an extra one in there. So we've got a carboxylic acid that has 16 carbons total. One of them is taken up by the CH3 and one of the carbons is taken up by the carbonyl group. Okay, so on the other side, we have 30 carbon atoms, and we already learned that this is where the bond is broken right there. So I'm gonna draw the alcohol with OH on the left side. We usually like to see it on the right side, but I'm just gonna keep it consistent. So this red O right here, we'll make it red right there. Okay, so it's picking up a hydrogen from somewhere. And then it says that we've got 30 carbon atoms. We haven't used any carbon atoms yet. So what we want to do is in parentheses put CH2, and how many of those? 29. And then what? Good. CH3. Are we okay with that, folks? Now I will not ask you to name those. For now. Questions for me?
So we just have to submit, put it into this version, like carbon, CH3, CH2, parentheses, 14, and the list goes on. Like
Yes.
that.
Yes. Okay, so triglycerides, folks, they're also called triacyl glycerols, and that's because you have a glycerol backbone, and you can see that right here. And you have 3 fatty acids, so that's your triacyl there. These are triesters, meaning they're esters, but there's 3 of them. And we saw that back here in the table, right here. Your triglycerides or your triacylglycerols, and we saw where we could break the bond in 3 different places because we had 3 esters within one big ol' molecule. So we're right there. Okay, so we've got 1 molecule of glycerol and 3 fatty acids, and remember fatty acids are just big what functional group? So this right here is R. What is that? When you have the R and then your carbonyl and then an OH. What functional group is that, though? It's a carboxylic acid. So fatty acids are just carboxylic acids that have a really big R chain. Do you remember me saying that? Maybe like 42 times about 10 minutes ago, but you're like, it's at the end of this lecture and she needs to stop talking because I can't take any more in and out of that, right? Oh yes, I remember those days. Okay, so this is a carboxylic acid, which is a fatty acid, okay? And it defines it right there for you. Carboxylic acid with carbon chains of 12 to 20 carbons in general, okay? Generally used for long-term energy storage. And we're Americans, so we do a really good job at this, storing our fat, right? Yes, we do. But other countries are catching up to us, so we better be better at it. Eat more bacon. Okay, so fat. Fat has 9 calories per gram. And notice right here it says kcal. And just in case you weren't paying attention in Chem 2A, that's a kilocalorie. The kilocalories are our dietary calories. So we also call kilocalories big C calories. Okay, so if you're looking at a nutrition label, it's gonna have a big C there. It's the same thing as kilocalorie. Like small c calories, those are not your dietary calories. Those are like way smaller, okay? So you have 1,000 small c calories in a kilocalorie, or 1,000 small c calories in a big C calorie. You guys remember that? Okay. Or you might have remembered that fat has 9 kilocalories per gram, and your protein and carbohydrates have 4 kilocalories per gram. Does that sound familiar?
Yes.
So that's why we went through the whole low-fat craze in the 90s. Because people were like, well, if fat has 9 kilocalories per gram, and carbohydrates only have 4 kilocalories per gram, then people should eat more carbohydrates, because there's less kilocalories or less calories per gram. But the problem with that is that we cut out all the fat from things and we just ate more of the carbohydrates, like we stuffed our faces with bread.
So
And what's that?
so it causes cravings where we're obsessively munching.
Yes, yes. And we all know that it does not help our diets to eat a lot of bread, right, folks? Yes. If it did, then pizza would be a diet food. But it's not, unfortunately. Okay, questions on this stuff? Good? Okay. So how do we put these together? So right here, glycerol, we can also call it a trialcohol. So you can see that you've got OH with an R group and OH with an R group. It's just that the R group is all bonded to each other. So we have glycerol, which is a trialcohol, and we're gonna bond it with 3 fatty acids. Fatty acids are what functional group, folks? The carboxylic acid. So you're taking an alcohol and a carboxylic acid, and you're making what over there? An ester. Now it looks weird because the R that's on this side of this O is connected to the R here, is connected to the R there. But if we just draw out a regular ester, this is backwards from how you're used to seeing it. You can see it there, okay? And these are carboxylic acids. So we're taking a trialcohol, 3 fatty acids, and we're making a triester, okay? And this is called a triacylglycerol. And you can see it down here in this diagram. So you've got your glycerol and you've got your fatty acids, and they are combining to give you a triglyceride there. Alrighty, folks? Kind of, sort of, maybe? Okay. Now, our simple triglycerides or triacylglycerols, you're going to have the same, and this is just the writing from the last time I did the lecture. I just didn't erase it. Nothing special there. They're all going to be the same. You can also have a mixed triglyceride where you have 2 of them the same and 1 of them different, or all 3 of them can be different. Okay? Questions? Good? All right. So it says fatty acids that form triglycerides are usually 12 to 20 carbons in length. You can have both saturated and unsaturated fatty acids. And that should sound familiar because we talk about saturated and unsaturated fatty acids and oils all the time because the whole diet thing and heart attack and blah, 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 blah. Right, folks? Okay. So what does it mean when it's saturated? Well, it means that all of your carbons have as many hydrogens bonded to them as is possible. And you won't see any double bonds in your R chains. So all of these are saturated fatty acids. On the next slide, it's going to show you unsaturated fatty acids. In your unsaturated fatty acids, what you'll notice is that you have carbon-carbon double bonds. Okay? One or more than one. So that means because the carbons are double bonding, they don't have the maximum number of hydrogens that they could possibly have, because if you're double bonding, then you have to remove one of the hydrogens to make room for that double bond there. So those are unsaturated. Now, the double bonds in your unsaturated fatty acids just cause little kinks in the chain, which cause the fatty acid chains to spread apart. And if you get farther away from each other and you're not packing close to each other, you tend to be a liquid at room temperature rather than a solid at room temperature. And that's on this slide right here. So notice this triglyceride right here, there are no double bonds anywhere in those fatty acid chains. And what happens when you have no double bonds is that your fatty acid chains can pack nicely and get really close to each other and do those van der Waals forces or dispersion forces, which keep those chains close together. If you have unsaturated fatty acids, somewhere in there you're going to have a double bond, which is going to cause a kink in the chain. And notice here how you have a large space between those two fatty acid chains. So if things are farther apart from each other, is it more likely that it's a solid at room temperature or a liquid at room temperature? A liquid, because of what we learned from basic chemistry, that if you have a solid at room temperature, those molecules or the parts of the molecules are probably really close together, and then when you get to liquid, they're a little farther apart. They're still pretty close, a little farther apart. And if you take it into gas, what happens? They're really far apart, okay? So that's why we have unsaturated fatty acids within our triglycerides, causing these oils to be oils or be liquids at room temperature, whereas the fats that have saturated fatty acid chains, they tend to be solid at room temperature. And our fats are usually derived from animal sources, okay? And our oils are usually derived from plant sources. Now we kind of use the term fat interchangeably. So sometimes there will be something that's plant-based that we'll call a fat. Like sometimes people call coconut oil coconut fat, but you don't hear that very often. Yeah. Any questions on this? No? We're good? Okay. So this one right here, it's got 3 fatty acid chains that are completely saturated, and you can see the melting point on this, where you go from solid to liquid, is 72 degrees Celsius. And this one over here, you've got double bonds, which make kinks in the chains, and so it's pushing the chains apart. So to go from solid to liquid, you only have to go up to -4 Celsius here, because they're already pretty far apart. So it is definitely going to be solid, liquid, or gas at room temperature. And room temperature in chemistry is 25 degrees Celsius. It's gonna melt at -4. This one's gonna be liquid at room temperature. Does that make sense to us, folks? It goes from solid to liquid at -4 degrees Celsius. So at 25 degrees, it's gonna be liquid. What about this one? Solid, liquid, or gas at room temperature? Solid. Because you have to take it all the way up to 72 degrees Celsius in order for it to go from solid to liquid. So at 25 degrees, this one's gonna be solid. Okie dokie smokies? All right, questions for me before we finish? Oh, apologies, I went 2 minutes over. I don't usually do that, so you'll have to forgive me. All right, no questions? All right, so Wednesdays, it is not gonna meet. There are no lipid questions questions on the quiz on mints? Those of you who have lab today, I'll see you up there. Those of you who have lab on Wednesday, see you then.
Good thing I drank coffee. Or I would have been asleep.
Yeah.
Thank you for listening. I did not know what the I didn't know. They usually thought liquids were liquids. I'll see you tomorrow. Tomorrow, Wednesday.
Okay, Wednesday.
Wait, so you do spring cleaning at home?
Yes, I clean like so.
My mom and I are actually doing spring cleaning now because the thing is, when it comes to dust and all that, we don't feel comfortable, you know, when it's not done.
That makes sense.
Yeah.
That makes sense for sure.
Yeah, but the problem is my dad wants to put tile, so we're gonna have to limit spring clean because then what's the point of cleaning when he's gonna make a big mess?
Mm.
See you around, Chris.
Bye.